So as Mr. Dersch said, I am a student of mathematics at Grand Valley, and this has been an idea that I've been interested in for a while. I've been kind of working with this idea, doing some research on it since high school, actually. And it never ceases to amaze me how many people think that math is about numbers and it's about following specific steps, and that essentially the point is to circle a number at the bottom of the page. And there's so much beyond math, and I'd like to talk about, or beyond that in math. I'd like to talk about that a little bit. So, a brief outline of what we're going to look at. What are the requirements for a language? Does math meet those requirements? And then why do we care? So first, what are the requirements of a language? According to the Merriam-Webster dictionary, a language is a systematic means of communicating ideas or feelings by the use of conventionalized symbols, sounds, or marks having understood meaning. So from this definition, we can see that there are 3 requirements to a language. A language must be systematic, a language must contain symbols with understood meaning, and it must communicate ideas. So now the question is, does math fit these requirements? So first, systematic. To be systematic is to have a method or a plan, to be logical. If you have a systematic approach to cleaning, it means you start over here in the kitchen, move to the living room, and then to the bathroom. Versus a non-systematic approach to cleaning would be starting in the kitchen, going to the bathroom, going back to the kitchen, and then to the living room, and just kind of bouncing back and forth. Now note, I'm not saying that there is a correct plan for how to clean. I'm saying that you have a plan. It doesn't matter what order you clean the rooms in, as long as you go from one room to the next. So math began with what we call axioms, or building blocks. They're things that we take to be true. And then the mathematics is when we take those 2 axioms, work with them logically through systematic manipulations, and come up with another conclusion. And then taking that conclusion and some other things, working with them logically until we come up with another conclusion, and so on and so forth. And as we work with math today, we are continuing this pattern of taking what we know, working with it logically until we can find something new. So by its very nature, math is developed from logical conclusions formed by systematic manipulations of its axioms, and is very systematic. So math fits the first criteria for a language fairly well. So next, symbols having understood meaning. Now, we've all seen these symbols, adding, equals, numbers, unknown numbers, or variables. We're all fairly familiar with these. But the symbols with meaning in mathematics go beyond just operations and numbers. When you get into upper level mathematics, you end up with symbols that mean phrases, such as the upside down A, which means for all, or the 3 dots, which means therefore. We also have symbols for the integers, or real numbers, or other sets of numbers. In both cases, we have symbols that have meanings that, in a sense, need to be translated into English, giving math criteria 2, containing symbols with understood meaning. The last criteria is communication of idea. Oops. So, I would like to ask you guys, what does it mean to communicate an idea? Anybody? Yeah, so something other than what we just saw. Or you can repeat what you just saw. That works too, because that was my mistake. Yes?
Taking something you're thinking of and being able to translate it to someone else who would then, in their sense, understand exactly what you mean by that.
Yes, and I love how you use the word understanding. My first point here is to pass along information. Information is moving from one person to another. But the word communication implies so much more than information moving from one person to another or from a source to a receiver. It also implies understanding. You want to talk to someone, not talk at them. Your goal is to make this information, your thoughts and your ideas and your feelings, understandable to whoever it is you're trying to talk to. So does math do this? Well, let me ask you, what does x equals y mean?
They're the same.
They're the same. How so?
They represent the same value.
They represent the same value. What else?
One can be used instead of the other.
one can be used instead of the other. X equals Y doesn't just mean they have the same value or the same properties. It also means they can be treated the same. In a sense, X is Y. They can be used interchangeably. Now let me ask you, what does Z equals 2W mean? Yes.
2 W's is Z.
Yes, 2 W's is Z. Is there anything else we can say about this?
Well, it also says something about W.
It says something about W too. Yeah. So there are actually a lot of things we can say about this. First is that Z is twice the amount of W. We can also say that Z varies directly with W. So if W goes up, Z will go up. If W goes down, Z will go down. And we can also say that Z increases twice as fast as W. So if W goes up by 2, Z will go up by 4. If W goes up by 5, Z will go up by 10. This equation, Z equals 2W, is communicating to us about the relationship between Z and W. It's, in a sense, a tool to interpret these two objects and how they will behave with respect to each other. Equations themselves give wonderful opportunities to see how things react in different situations. So now the understanding. Is this understandable? Now, I'm not asking you, do you understand all of math right now? I'm asking, do you understand that when I say Z equals 2W, I'm saying that they vary directly, that that Z will increase twice as fast as the other. Or when I say that X equals Y, that they can act the same.
Well, we probably don't understand because we've had algebra.
Yes.
A 5-year-old probably wouldn't know what that meant.
Yes, but a 5-year-old also wouldn't understand most other languages, or most bits of English. So we don't ask anybody to know all of the vocabulary of English in order to say they understand English. We ask them to be able to understand a large majority of it, or a good chunk of it, so that if I was speaking English, they would be able to understand me. I believe it's the same thing with math. You don't need to understand it all in order to speak math or to understand math. You just need to be able to understand bits and pieces and be able to work with them. And there's actually something really interesting that comes out of this. Equations and manipulations of them tell us more than just moving the terms around or what the original equation told us. In fact, through manipulations, an equation can tell us more about its components and their relationships with each other than simply reading the equation itself. Manipulating an equation is like having a conversation with it. When you see an equation, going back to our Z equals 2W, by moving pieces around, say by dividing by 2 and solving for W, we are in a sense asking a clarifying question of our original equation. We are asking, well, what does that say about W? And by asking the question and moving the pieces around, the equation responds back to us by giving a result. So equations in mathematics not only communicate from one person to another through writing it down and having somebody else read it, but it also communicates from the equation itself to the person working with it through seeing an equation, moving the pieces around, and getting a result back. So what have we shown so far? We've shown that math is systematic, math has marks with understood meaning, and math can communicate ideas. What can we then conclude? That math is in fact a language. Not that it acts like a language, that it is in fact a language. And there are some really great conclusions that we can take from that. So, why do we care? Not all of us here are mathematicians. Not all of us are in or going into a field that requires mathematics. Yet this idea is extremely applicable to all of us. And there are two ways that we can see that. First, by seeing math as a language, we will approach math differently. And second, we will teach math differently. All right, so first, approaching math differently. Manipulations have meaning. Math is not about following predetermined steps. Each step has a purpose that can be understood and could provide clues to your answer. Don't blindly move around pieces just because it looks like what your teacher did in class, or it looks like what the book is doing. Ask yourself why. Why did I take this step, and what did it tell me? Read the equation after you move it around. What is it saying about each of the pieces? The point of mathematics is not to circle a number at the bottom of your page. It is about logical thinking, being able to reason through situations or think abstractly. It is about the process of understanding, not the answer itself. Next, solving an equation or proving a theorem should be like telling a story. There is more than one way to tell a story. Likewise, there's more than one way to solve a problem in mathematics. The focus should be on communication. When you finish a problem and you get your answer, ask yourself, all of the steps I took, did they properly communicate that this answer is correct? Or when you're proving something, did I fully clarify everything that I was stating? And did I make logical conclusions? Or did I jump from one idea to another without a connection? And then again, ask yourself, did it communicate what I wanted? All right, and finally, under approach math differently, math allows us to communicate with the natural world. There are so many equations out there that describe nature. And since math is a language, those equations can allow us to hold conversations with nature itself, because nature speaks mathematics. So mathematics describing the world around us gives us a chance to hold a conversation with nature. How cool is that? So nature doesn't speak any other language. It speaks mathematics though, and through it, it tells amazing stories about patterns and about things that happen and about things that don't happen too. I have a few examples of this here. Everything from falling objects, ripples in a pond, to what we find beautiful can be described with different things in mathematics. For the free fall equation or wave equations, we find that if we are given a starting point, we know exactly what's going to happen in the end. And the same in reverse. If we know how things ended, we know exactly what happened at the beginning. And then with the Fibonacci sequence, there are patterns to what we as humans find beautiful, what we consider to be beautiful. And one of the ways in which that is represented is actually found in the sequence of numbers discovered by Fibonacci. Through the Fibonacci sequence, we get the golden ratio and the golden spiral, and those are things that we find in the spin of a galaxy or in a nautilus shell, or in the angles between which flower petals grow. And as you go into this, you see more and more that it not only is described by these numbers, but that it has to fit that pattern in order for the plant to live and survive. And that is just absolutely amazing. Right? So the other reason why we care is because it allows us to teach math differently. So the purpose is not to find x. There are so many jokes out there about kids asking algebra, stop asking me to find your x. She's gone and I don't know why. And as funny as that is, it's not the purpose. It gets at the point that students are in math class trying to find x. They're not in math class trying to learn to think logically, how to make connections. In English, we don't write a sentence for the sentence's sake. We write a sentence to communicate an idea or to state something. It's about communication. Should be the same in mathematics. Next, there should also be more focus on solving a problem as a result of understanding the problem itself, instead of understanding preset steps. As a teacher, this is super important, because if you explain how to solve a problem in a specific way, but then not talk about how there could be other ways, or not talk about what is going on in the problem, your student will sit there and they'll memorize those steps, and then they'll go to another problem and have absolutely no idea what to do. Because in their mind, if this problem over here is slightly different, it doesn't fit the steps that they were trying to do in class. Versus if they understand what's going on, they will be able to take that line of reasoning and then apply it to multiple different areas, both in math and outside of math. Remember, you can tell a story multiple ways, the same way you can solve an equation in multiple ways. So overall, math class shouldn't be about how to do math. It should be about how to think in math. Again, just like in a language, when you're learning Spanish or French, you're not taught to take the foreign sentences, translate it into English, figure out an answer, and translate it back. You are taught to think in that language and forgo English altogether. It should be the same for math. We shouldn't be trying to take math out of, or take our manipulations out of mathematics, figure out what's going on, and then put it back in. We should be trying to reason with what we have here. Thinking in math involves seeing connections and pathways to your conclusion or answer. So being able to see ahead and reason through the problem using logic. So what does this thinking in math look like? It means not relying on memorization. If your student memorizes, or if you as a student, or if you have a student that just memorizes a set of steps, one, our memories aren't very reliable, and it's easy to get things switched around, so you end up with an equation or a process that isn't entirely correct. And also, when you're taking a test, your memory's the first thing to go. So everything that you work so hard to remember verbatim is just not there anymore. Next, it means understanding why. Asking yourself after each step, why did I just do that? And was it helpful? If you're trying to solve a problem on your own, and you see the equation or whatever it is you're working with it, you take your first step, ask yourself, did that get me closer to my answer? If it didn't, then you already know you're on the wrong path. And lastly, working with what you know. If you don't understand or remember the equation that you tried to memorize before, look at what the problem it is you're trying to work with and say, what are the pieces? What can I do with them? What do I know, and what can that tell me about what's going on? I'd like to show you an example of this. We've all hopefully seen simultaneous equations before. So I have an example of that right here. 3y equals 8x minus 32. And 7x plus 9y equals 28. Now in algebra class, we learn 3 different ways to solve this. You can solve it by graphing, substitution, or addition. However, what if you don't understand those, or you don't remember how to do them? By thinking in math, we can solve this without any of those processes. So, thinking in math here, we see that both of these equations are talking about the same objects, x and y. But they're saying different things about x and y. Here it's talking about 3y. Here it's talking about 7x plus 8y. But what if we could get them to say the same thing? So over here, looking at this 3y, I can make that into a 9y by multiplying it by 3. This whole thing by 3. So we get 9y equals 24x minus 96. So now, okay, so we're talking about 9y. We need to add this 7x. So on this side, we get 7x plus 9y equals 31x minus 96. All right, so now we have two equations that are talking about the same exact thing, but they're saying different things about them. Well, if 28 is this, and 31x minus 96 is that, that means that we can equate these two sides and get 31x minus 96 equals 28, which gives us 31x equals what? Yes, 124, which means x equals 4. Now we go back to the original equation here to figure out y. I'm going to switch colors for the sake of seeing. So we have 3y equals 8 times 4 minus 32. So 3y equals 32 minus 32, which equals 3y, which means 3y equals 0, y equals 0. So without using any of the preset steps that I learned in algebra and understanding what the equations were saying and what they were talking about, I was able to find answers for both x and y. So, what have we learned? We have learned that math is a language, that working with equations is like having a conversation with them, and that math is about understanding, not steps. And hopefully through these ideas, both applied in the realm of teaching and in the realm of learning, we can change this preset understanding that mathematics is about steps and about numbers, and that the purpose of math is for math itself and doesn't go beyond numbers or math class. And maybe then we'll be able to start developing more logical thought processes in the world and in reasoning around us. Questions? Yes?
Okay, so you said math is a language, and some people are better at like languages, but they're not always as good as math. Is there a reasoning, or your reasoning or thought process, why they're not as inherently good as math as they are good with languages? No?
Our brains fundamentally see things differently. So someone that is good at a language understands how languages work. Math right now is presented as a set of steps that you need to follow in order to get a number circled at the end of your page. So if you're not able to think abstractly and realize what's going on in each equation or each manipulation, then you see these sets of steps and you think, oh my word, I have to memorize this. I'm not good at memorization, or what if I forget? And then that stresses people out and plays into the fact that people aren't as good at math, that they're thought that they're not as good at math. So by viewing math as a language, I'm hoping to hit that group of people that's good at languages but not good at math. So if we teach math as it is a language that just works slightly different, then they're able to take what they know about languages and apply it to mathematics to help them understand it better. Anyone else? Yes.
When you referred to thinking in math,
Yes.
I did take quite a few years of French at one time in my life, and I have very little to show for that. Not to embarrass myself if I go to Quebec. But I did get to the point where I was just sort of maybe fishing or something with my dad. I could find myself thinking in French, which is actually kind of scary on one. And my teacher at the time said, well, you really made it if you're dreaming in that language. That never happened to me. I have a question for you. Have you ever, in your dreams, have you ever solved a math problem? Have you ever figured something out mathematically that was bugging you? Just as like, I don't know how to get this done.
Yes, and it was actually for your class. I was working out a problem all day. Yeah.
Oh, please, if you would like to go ahead, because now I'm really curious.
I don't remember what the problem was. I think it was for the differential equations linear algebra class. I was working on a problem all day and could not figure it out. I finally decide I can't think anymore, I need to go to sleep. I laid down, I fell asleep for like 5 minutes, and I woke up with the answer.
Do you remember if it was linear algebra or differential equations? There's a reason for that question.
I'm pretty sure it was the differential equations, like the optimization of
And
pouring, whatever that
This is
was.
painted in broad strokes, so I'm about to say it's not that accurate. But differential equations, there is a lot more of, here are the rules. Follow them, and you could come up with an answer that you put a box around at the end. It's not just that at all, but some of what we do in an introductory course looks like that. Linear algebra is a lot more ideas and proof-based. And the idea that one needs to have an incubation period in mathematics, which could involve sleep, that actually has happened. I saw some nodding heads. I don't know if there's anyone else that wants to share their solving math in their dreams, or you were nodding your head with Shanna. Shanna's my office. I can bug her a lot. So do you have anything you'd like to share? Or?
Well, we were epsilon delta proofs, you know, it was gibberish to me. Why on earth? This is nonsense. This is total nonsense. What on earth are they talking? Literally, it was Greek to me.
Epsilon and delta.
And one night I went to sleep and I dreamt the answer to one of the problems I was working on, and it would just like suddenly miraculously, oh, that's all they're doing. They're working backwards until they know what it is, and then they've got it. And I remember waking up, and I woke at that time I was married, I woke my husband up and made him listen to me. Otherwise I probably would have forgotten. But I remember being so excited, I was like, oh, you know, they're kind of cheating, really, but I get it now. And it was just literally hearing the answer. So yeah, I totally get it.
More kind of comment or going along with what you're saying. I was reading a book a while ago for a class I took that was about connecting reading with teaching math. And made me think of one thing. They were talking about how elementary school teachers often try and teach kids understand math by getting them to look for the keywords. Meaning, you know, that more means add and less means subtract, and that obviously is not true. And I was thinking that it's funny that kind of what you were saying about what people think, you know, that they're teaching for understanding isn't necessarily actually understanding what it means.
Mm-hmm. Yeah, and it's really hard at the youngest ages because their abstract thought is not there yet. But what's really sad is when they take the same reasoning in the elementary schools and put it in like high schools.
Yeah. I kind of think I've been thinking about math as a language for quite a while. In fact, I was interviewed for a job, and the dean was an English teacher, and he said, I want you to explain to me, I'm an English person, explain to me how math is like English, and this is what I came up with. It's a language. When you're learning a language, there's understanding the structure and learning to communicate, and there's vocabulary.
Yes.
So how do you see that relating to math as a language? Do you think you really need to get some vocabulary in order to begin doing the communication, or does the vocabulary come as part of that? Or
I haven't thought much about it, but what I have kind of come up with is that the vocabulary isn't just the numbers and the symbols. It's like basic arithmetic. So what we teach elementary should be considered vocabulary. So then when they get to algebra in high school, that should be more of the communicating and understanding what's going on. So there is kind of this level of you need to understand the vocabulary first. Just like when you first step into a classroom it's helpful to hear the words, but you have no idea what's going on until you get a list of vocabulary kind of under your belt that you can start working with. Does that answer your question? Yeah?
Comment and a question. While us oldsters were growing up, we always had the opportunity to go out and play during school. It was called recess. It was different from the lunch hour. And I'm just wondering if that gave us the opportunity to like just mull over what we were just doing in math class and then come back in and understand it better. Because we cut recess out from a lot of schools to save money.
I don't know that adding a recess would necessarily help you understand math unless you are a good student and you were purposefully thinking about what you learned over recess.
Right.
But most kids, when you say go out and play, school is the farthest thing from their mind.
Right. Well,
So having that incubation period is
taking
helpful.
naps or, dreaming about this, so it's kind
Yeah.
of like a way of getting away from it and then coming back.
Yeah.
So.
I do think having a break is very helpful. In a lot of my proof-based courses, the number one way to solve a problem was go take a break and come back in a minute. So I get that that is extremely important
Right.
and would be helpful.
And here's my question. You start off by saying x equals y.
Mhm.
But the equal is a representation of the verb is or are. And I'm just wondering, how are we even thinking about changing how we're communicating math to kids when they don't understand certain things like, equal is so simple, but there are, you showed some other symbols up there. It's like, well, how am I going to remember that?
Yeah, well, that's why a lot of those symbols don't come up until you take proof-based courses. But, if I'm understanding your question correctly,
It's the science of it, and I'd just like to know, is it just beginning, or are there people out there already like pushing forward a different language?
the idea of math as a language?
Yeah.
I have not found much literature out there written on this. That's one of the reasons why I was so drawn to the idea, is that it's so unknown. There are people out there. There's a professor at Grand Valley who's done some research and some talks on it. I know there are papers out there and other people thinking about it, but it's definitely a new idea. And with the need to reform our thinking of math in the high schools and middle schools specifically, I think that this idea coming out is very important.
Yeah, we all have a niece or a nephew or know somebody who it's just a real struggle to, grab those concepts and do well on a test, and they, they struggle and they get C's and D's, and it's like, geez, if only there was a way.
Yeah,
Maybe this is one of the ways, I don't know.
hopefully. I'm trying to integrate this a little bit more into my teaching. I teach for a homeschool co-op, and I'm trying to use these ideas more and more, but then again, it's so widely unknown that putting it directly into the text would be difficult at this point. Any other questions?
You told me about this and I forgot the details, so you'll have to help me. You got, this summer.
Yes.
What are you doing this summer?
I got funding to do independent research, or mentored independent research through Grand Valley.
And what will be the subject of that research?
The combinatorics of RNA. So we're counting the different ways that a specific RNA strain can fold.
And I asked that because I wondered if there was going to be any connection between that and communication. And I realize we're talking about two very different areas right now. However, when you do something like that, there is the research that you will do,
Mm-hmm.
and then there is the idea that you have to communicate that with others.
Yes.
Partly because if you want more funding someday,
Yeah.
you have to establish a baseline which says this was worthwhile. But also partly because, and to me, why do I enjoy teaching? I think one of the main reasons is I like to share. So, so the communication idea, I think, in this case, really fits very well with your summer research, because you want to be able to communicate what you're doing so that you can share it with others.
Yes. Was there a question in there?
I was wondering, no, I didn't know what the observation, or what the research was going to be on. So
Yeah.
I was wondering if maybe it's going to be related to what you're talking about here today. And peripherally it is, but not directly.
It's not directly related, no. But because this is something that I've been working on for so long and I want to see how it relates in different areas, I'm definitely going to try to fit it in there quite a bit. The basis of our research is kind of ideas in discrete mathematics, so counting. And discrete is a lot of explanation versus like linear algebra would be more computations. So that's kind of helpful in the sense that you see something that's going on and you can work with it in algebra, but then you need to figure out what is that actually saying about the piece that you're working with. So it's in there just a little bit.
I have a question.
Yes.
Sorry to do this to you, but I just have to ask
What?
because, you know, us mathematicians, we just love definitions, right? And so, towards the beginning of the presentation, you kind of outlined what I believe Webster
Yes.
dictionary says about the word language.
Yes.
And so in there, and I don't necessarily expect a direct answer, but I just need to ask. In the definition, it says communicate, and then in there it says communicate feelings, or
Yes.
like what's your take on that? How would you interpret that?
I think there are multiple different ways to interpret that. So you can definitely communicate frustration and anger through very impossible problems, but you can also communicate satisfaction and just this feeling of overcoming when you finally figure it out. But this, I don't know that this would work for everybody, but definitely as mathematicians, we can communicate a lot of different feelings through mathematics. So one of my favorite equations, the Euler equation, e to the power I times pi plus 1 equals 0. This equation, and I've talked to other people that think the same thing, is just so satisfying. It's so simple and condensed, yet means so much. And I think through equations like this, you can communicate a certain level of feelings for what's going on. But again, that would mostly be for mathematicians only.
Well, I mean, if we go math being a language, then it's for everyone then, right?
Yes, but notice it said communicate ideas or feelings. So it's not a requirement. That's why I didn't cover it, otherwise I would have. Yes.
Have you delved into how music plays a part in that?
I've done a little bit. I play a little bit of piano, and I've definitely messed around with how the different note number combinations relate to like the harmonics in mathematics. And I've worked a little bit with waves, but I haven't done a whole lot with that. There's definitely a lot there.
I think in the analogy of language, when you're speaking about communicating feelings, in essence, when you're learning a language, you don't necessarily have facility with the language to really share nuance, and maybe don't really understand what is being expressed as well as when you gain more sophistication, which is why an equation like that probably doesn't mean much to a kindergartner, but means more to a more experienced mathematician.
Yeah, because the levels of complexity are better understood by someone who's worked with pi or with imaginary numbers. Do you have any other questions? Yes.
Would you say that our systematic approach of teaching mathematics from the beginning of, say when you start learning math in the elementary ages all the way up to the collegiate level, would you say that that would need to change along with what you're implying in terms of teaching it more as a language? You know how we start with, basic, addition, subtraction, moving our way to fractions to things, or would you want to change that up in a sense to teach kids in a different outlook and, teaching, say, fractions first before addition and multiplication, anything like that?
I don't know that the order in which we approach things actually matter. I do think that you should teach integers before you teach fractions because fractions involve the relationship of two integers. Overall, I think that elementary and the base level, learning math as a list of steps at that point is okay because that's all you can understand. But once you get into high school or even into later middle school, if you're continuing to think that that is all that math is, that's where the issue is. When you are starting to develop that ability to think abstractly around the age of 13, you should be really pushing yourself to understand what's going on in the equations themselves instead of just seeing, I do this, then I do this, then I do this.
Katrina, thank you so much. That was wonderful.
Thank you.